So this Stats Weekly application to sci-fi rather than games, when I read it, I was struck by just how great a description it is of what it would be like to be inside a Poisson process, basically, to be waiting for something that has this memoryless property. So if you remember, the exponential distribution is the amount of time it takes until the next event in a Poisson process. That's kind of the definition of this random variable. And it's obviously going to be a continuous random variable because time is continuous. And it's going to be non-negative as well. So you're not going to go backwards in time. This how long you have to wait until the next event. But the Poisson process, one of the assumptions about it is that everything is occurring at a constant rate, and the process has independent increments. So what happens in one time period cannot affect what happens in another non-overlapping time period. And what that means is that the Poisson process itself is a memoryless process. So whatever happened in the past doesn't matter, it doesn't affect what happens in the future at all. If it did, it would violate the independence assumption. So what that means is, if something is actually following a Poisson process, then no matter how long you've been waiting for something, that doesn't help you get the next event any sooner. And that's really weird because, nothing really perfectly follows a Poisson process in real life. Like buses don't run on a Poisson process, they run on a schedule. Sometimes they're late, but it's not really a Poisson process. Nothing probably is exactly a Poisson process. Lots of things are close, but nothing's perfect. So this story just had a really cool description of what it would be like to be in a Poisson process and be waiting for the next event to happen in a way that has this memoryless property. So the story, again, is by Greg Egan. Here's a link to a collection of short stories that he wrote that has this one in it. And the story itself is called Into Darkness. It's about this phenomenon that affects the town where this person lives called the intake. Ooh, sci-fi sounding. And it basically affects the area for an exponentially distributed amount of time. And eventually it ends, but waiting for it to end is like waiting for the next event in a Poisson process. No matter how long you've waited, it doesn't affect how much you get to wait in the future. So these are just a few lines from the story. The intake's manifestations obey exactly the same statistics as a radioactive nucleus with a half-life of 18 minutes. 75% last 6 minutes or more. I've memorized the probabilities right out to an hour, 10%. A mere 10% of manifestations last for an hour or more, but of that 10%, half will still be there 18 minutes later. For someone inside to ask what the odds are now, he or she must be alive to ask the question, and so the probability curve must start afresh from that moment. History can't harm you. The chance of having survived the last X minutes is 100% once you've done it. Just so cool. In the story, the reason that this person has to know these probabilities is that they're a specialist that goes into this intake to rescue people and help get them out. So that's, I should have given that context before. So this is just, again, not the point of the story, but all of this is actually part of it. And I wanted to see if we can verify some of these calculations. So first of all, we're told that the first sentence here, the intake's manifestations obey exactly the same statistics as a radioactive nucleus with a half-life of 18 minutes. And it also tells us that 75% last 6 minutes or more. And these are two different statements. First of all, we can think about measuring the amount of time this intake lasts. If we measure it in minutes, we have it as an exponential random variable, and we have this parameter theta. And we're told that the half-life is 18 minutes. So a half-life is basically the median of the distribution, not the mean, not the average, but the half-life. So the probability of lasting more or less than 18 minutes is exactly 0.5. So from that information, we can actually solve for the theta, the parameter for this exponential distribution. So here we go. So we're told again that the half-life is 18 minutes, which means that the probability x is greater than 18 is 0.5. Again, we're told that the median is 18 minutes. And we can also write that as the probability x is greater than 18 as 1 minus big F of 18. Using the CDF of an exponential distribution, that's 1 minus e to the negative 18 over theta, which the 1 minuses will cancel out nicely, and we just get e to the negative 18 over theta. And so we have these two expressions for the probability x is greater than 18. We know the probability x is greater than 18 is 0.5, and we know it's also equal to e to the negative 18 over theta. And so we can equate these two, set these two equations equal to each other and solve, and that gives us a parameter of 25.96. So the average time that the intake lasts is about 26 minutes. but the median time that the intake lasts is 18 minutes. Those are not the same. The mean and the median are not the same for the exponential distribution. It's a skewed distribution. It has a long tail. So that's one thing that we can do. And then we can actually also verify this, the second part of the statement here. 75% last 6 minutes or more. So let's see if we can calculate the probability of this intake, x, lasting for 6 minutes or more. So the probability x is greater than 6. Well, that's 1 minus big F of 6. Plug it into the values here, and we get 0.7937. So it's pretty close. He says 75. The actual number is 79%, but that's okay. Rounding, not a big deal. So that's kind of neat. Whoever wrote this story, Greg Egan, obviously did some math, or had someone do some math for him to figure it out. Here's another cool thing. I've memorized the probabilities right out to an hour, 10%. So we can do the same thing. We can find the probability that the intake lasts longer than 60 minutes. That's again 1 minus the CDF evaluated at 60, which is 0.0992. So really nice and close to 10%. Pretty cool. Good job on that math. And then here is the neatest part. A mere 10% of manifestations last for an hour or more. That's what we just calculated. But of that 10%, half will still be there 18 minutes later. So essentially, what we're looking for is, given that it's already lasted an hour, we want the probability that it lasts another 18 minutes or more. So 78 minutes total, at least. So we're looking here for a conditional probability. The probability x is greater than 78, given that x is greater than 60. Well, we can actually evaluate that using the definition of conditional probability. It's the probability of both being greater than 60 and greater than 78 on the numerator, and then divided by the probability of being greater than 60. But for the numerator, if it's greater than 78, it's automatically also greater than 60. So the numerator just becomes p x is greater than 78. That's the intersection of those two events. And then again, we're dividing by p x is greater than 60. Sub in those values, and we will get exactly 0.5. And that shouldn't be a surprise, because this is just the memoryless property applied, right? If we know that this property follows an exponential distribution, which is what we're told here, then the fact that we've waited an hour makes no difference in terms of how long we're going to wait in the future. Given that x is greater than 60, the probability x is greater than 60 plus 18 is just the same as the unconditional probability that x is greater than 18. So, and that we had found before was 0.5, or actually we were told that. So that's kind of how the memoryless property would manifest in this case. That, like, no matter how long you've been there, half of the things that you're in will still be there 18 minutes later. So even if you're in there for 2 hours, 10 hours, 100 hours, whatever, there's sort of never any change in the future prospects of this intake. And you can never be sure that the end is near. It's kind of freaky, actually. If you're waiting for something with an exponential distribution, no matter how long you wait is not going to help you get it any sooner. So then this last quote is sort of like how the memoryless property makes sense, that once that history can't harm you. Once you've survived that last period of time, you're alive right now, and so you have to be alive to ask the question, and the future distribution is the same as it was from the very beginning. So the story, again, is not just about the exponential distribution. I promise it's an interesting story. Definitely check it out if you like sci-fi, and lots of the other short stories in that anthology that I linked to are very, very cool as well. All right, any questions about this? It wasn't really an application to gaming, but I thought it was a neat application of the exponential distribution. So the next thing I want to do is just briefly talk about utility functions for our machine learning idea of the week. Recall, of course, from earlier on in the videos this week in Chapter 8, we talked about transforming continuous random variables. So in other words, if you have some random variable x that has a PDF that you know, or a CDF that you know, and you want y, which is some function of x, call it h of x, how can we find information about y? Like, we'd love to have the CDF of y, we'd love to have the PDF of y, we'd love to be able to find the mean and variance of y, all of that, when all we know is x. And a couple of people actually on Piazza have asked, like, why, what is the point of this? Why are we learning this? And that's a valid question. So there's lots of cases where the thing we're interested in might not be the variable itself. So we might be modeling, let's say, x is the price of a stock, but we don't care about the price of the stock. We maybe have an option on that stock, and the payoff of the option is a function of that stock price. So we could have a distribution that we care about, which is related to another distribution, but not exactly the same. So it's a function of that other distribution. And then if we can find out information about the price of the stock using whatever distribution we like, we can then find out information about what we care about, which is the payoff of our option. That's just one example, but there's lots of others in lots of different situations. But the another idea, actually, which is what I'm going to talk about next week on the stream, is you can use this idea of transformations of random variables to randomly generate variables from different distributions. So the idea of random number generation, or RNG, in gaming or in lots of other applications relies on this fact that we can transform continuous random variables in this way. So more on that next week for sure, but I want to just today talk about utility functions. So in general, what we've learned in chapter 8, that if we have x and we want y, then we follow the 3 steps as follows. We write the CDF of x in terms of the CDF of y. So we write like the CDF of y, ooh, sorry, my hand is shaking, is the probability that y is less than or equal to little y. And then you manipulate that in some way to get it to be a probability involving x. So this is, again, the probability that h of x, whatever our function is less than or equal to little y. And then you do whatever you need to do to that function to isolate x and then have a probability involving x. So you go from there, and it depends on the function h, it depends on the range of x, whatever, but you isolate x here, and so you have a statement of the probability involving x for your CDF of y. Then step 2, you use what you know about the CDF of x, and then that gives you the CDF of y, and then you differentiate with respect to y to get the PDF. And the other cool thing is you can do this in either order. So you can actually differentiate first and then sub in what you know about x, or you can sub in first and then differentiate. It works in both directions. You just have to be careful when you differentiate with respect to y first. You probably will need the chain rule. So just be careful about that when you're differentiating. Make sure you're using the chain rule properly. And then again, sub in the information that you have about the PDF of x. Or again, the way it's written here is sub in first the CDF of x and then differentiate with respect to y. So just be careful about using that chain rule properly. And then the last step, or honestly you could do this first, is determine the range of y. And that's going to depend on both the range of x and on the function, that function h. So if x is, let's say, between -1 and 1, and y is x squared, then x going between -1 and 1, when you square that, you'll get a number that's between 0 and 1. So the range of y would be 0 to 1 if x was between -1 and 1 and y was x squared. If like x goes from 0 to 10 and y is like 2x cubed, then the range would go from 0 up to 2,000. That's a weird choice of a function, but whatever. So it depends on both the range of your original random variable and on what the function is, what the transformation that you're doing. And there's no probability involved in that. That's just functions, like first year probably high school level calculus or pre-calc or functions or whatever it's called. Just thinking about what is the range of your function and then what values does it map to. So I guess the range of x is the domain of h, and then what is the range of h over that domain. So that's sort of a review. So this idea of being able to find information about one random variable given information about another, it often comes up in lots of different ways. I mentioned a sort of a stock option payoff as one, but another great example is in machine learning, something known as a utility function. So what a utility function does is it basically assigns a value, a numerical value, to the outcome or the result of an algorithm. And it represents in some way how good a job that algorithm did. So if it's like a translation algorithm, like something of natural language processing, maybe it's the percentage of words that are errors or something. So there's some other way to validate it. But the way that you define goodness depends on the situation. There's not always only one definition. But a really good way to think about it in a way that's concrete is to think about utility as measuring the happiness that you get from a certain amount of money. So this is often sometimes used in economics as well, the idea of the utility of some kind of business venture or payoff or something. So it's not just about the amount of money that you get, it's about how happy that money would make you. Now, we're going to define sort of the basic idea and the requirements of a utility function. We'll call u, this function, u of x, is the utility obtained from having a wealth of x dollars, and we'll call that result y, just to use the same format here. Now, one thing that's fairly obvious is that u of x is going to be an increasing function of x, right? You would, all else being equal, you would rather have a little bit more money than less money, right? And maybe, it's not maybe not necessarily strictly increasing, maybe it's a non-decreasing though. So that's usually a requirement of utility functions, that if you have more wealth, your utility of that is higher. But the other thing is that it doesn't increase linearly. Like, you're not exactly as happy as the amount of dollars you have. So if somebody had literally no money at all and you gave them $10,000, they would be absolutely thrilled. I mean, I would be. But if someone who is a billionaire, if you gave them $10,000, they wouldn't even notice. They might just think it's a rounding error, like, who knows? So the more money that you already have, the less each individual dollar, like, affects your happiness, basically. This has a name. This is called the principle of decreasing marginal utility. So, like, the more you have, the less each individual amount means for you. And that, in terms of a mathematical definition, means that the second derivative of the function is negative. So this utility function, it's got its first derivative being positive. That means it's an increasing function. And its second derivative is negative, which means it's increasing, but at a decreasing rate. So it's kind of going to look like this, like that. Oh no, can you see that? Yeah, there we go. I mean, that's not a perfect, it doesn't have to be like exactly that shape of curve, but if here's your wealth and here's your utility of wealth, it's increasing. It's never going to go back down, but it's increasing at a sloped, shallower and shallower rate as you go up. So sometimes the logarithm is used, like log utility is often used as a simplification. And every person's individual utility function is different. And again, if you were doing an algorithm, how you set that utility function would depend on the impact of being wrong in a different direction. So it's not necessarily always going to follow these exact rules, but in the context of money, yeah, you'd want it increasing with a decreasing decreasing slope. So basically what's happening is, if you know that this strategy or this algorithm will result in an amount of wealth x, and that has some distribution with a PDF of little f of x, then you can use this technique up here to figure out the distribution of the utility that's produced by that wealth. So if the wealth itself is random, the utility is also random, and you can find out the range of it, you can find the probability density function of it, you could also find the mean and variance of it, you could find the probability it's bigger than a certain threshold, you could do whatever you like once you have this PDF of y. One other cool fact is that if you have a function with these properties, so a positive first derivative, so an increasing function, but a negative second derivative, so it's increasing but at a decreasing rate, that's known as a concave function. And concave functions have the property that the expected value of the utility is always less than or equal to the utility of the expected value. And that's kind of hard to understand here. We're assuming, obviously, here, if the second derivative is negative, then this is definitely not a linear function. So u of x, you can't just swap the expected value and the function. You can only do that for linear functions. But in particular here, it's saying that if we have an unknown thing and we want to know what's the average utility of that thing, that's going to be less than the utility of the average amount. And that's a risk thing, right? If you were given the option of either $100 or $0 with 50% chance each, or here is $50 for sure, most rational people would take the $50. I mean, maybe some people are a little more risk-seeking, but most rational, risk-averse individuals would rather take the guaranteed money. If it was something else, like if it was here $25 or 0 or 100 with a 50-50 shot, then it's like, well, on average, we would expect more, like in terms of expected value, from the taking the gamble, taking the chance. But there would be a number where you would be indifferent between those two things, and that would be the expected utility of that payoff between either $0 or $100. So that's the idea of this. This has a name. It's called Jensen's inequality. You can look it up if you like and you want to know more. The proof of it is probably reasonably accessible, but not something you need to know for this class. So basically, if we have some kind of machine learning algorithm that's trying to maximize the utility function, what it's going to do is choose values, choose parameters to fill this in to maximize the expected utility of this uncertain outcome. And it's not necessarily, by Jensen's inequality, it's not necessarily going to be the same thing as just looking at the average case and then doing, maximizing that. So a great example of this isn't really machine learning, but like sorting algorithms. You could basically think about like how it performs for an average list versus how it performed for really, really close to sorted lists versus really, really, really unsorted lists, and think about optimizing for that. Like you would make different choices if you knew that the list was always unsorted in a particular way than if you had a sort of spectrum of possible amounts of original sortedness that the list would have. All right, so that is everything for the machine learning idea of the week. Again, the idea of a utility function comes up in lots of different areas, economics, AXI, as well as machine learning. And it's just an example of this transformation process that we now know how to do, where we start with one continuous random variable x, and we want to know about y, which is some function of x. We can now get the mean, variance, PDF, CDF, whatever, of y, knowing this transformation technique. One question was for CAA2 in R generating uniform random variables. It only keeps, it looked like you said 10 decimal places. That is totally fine. So that is, oh, my face is in the way. Here we go. It only keeping about 10 decimals is totally fine. Yeah, whatever's keeping track in the background may have more precision than that, and it may just only bother keeping 10. You can probably tell it to keep more precision, but 10 decimals is just fine for the purposes of this exercise. Yeah, great. Thanks for the question. The other question on Piazza, and I see one on here as well. The other question was, can I go over the difference between theta and lambda of the exponential distributions? I absolutely can. So theta versus lambda, the final battle. Okay, so they are both very closely related to each other. And the way to tell which is looking at the units, actually. So theta is the parameter for an exponential distribution, the way we use it. And it's also the mean of the exponential distribution. And it represents the average waiting time in between events. So it's measured in time between events. Or distance, I guess. Like if you were using a Poisson process over like space, then it would be like the distance between events. On the other hand, lambda is the parameter for the Poisson. I'm sorry, I should have organized this better in a table. It's the mean of the Poisson. For a 1 unit, I guess, like over 1 unit of time. So it's the mean number of events in a Poisson process over 1 unit of time. And it's measured in events per unit time. So that is the key for how you can tell the difference between whether you're given lambda or theta. If you're given a parameter that's the amount of time it takes for something to happen, then you're given theta. If you're given something as a number of events that occur per unit time, then you're given lambda. And the relationship between them is a reciprocal relationship. And that should make logical sense, right? The more events that are happening per unit time, the shorter time it's going to be in between those events. And similarly, the less frequent the events are occurring, the lower lambda is, the longer you're going to have to wait in between events. So theta is 1 over lambda, and obviously that means lambda is 1 over theta. So that's the relationship between them. So hopefully that gives you a sense. The key, again, is to think about the units that you're given. So if you're given a question and it says whether the question is about a Poisson distribution or an exponential distribution, either way, both distributions could be involved in some way, or even other distributions. But thinking about what you're given, you want to look at the units that it's measured in. If it's measured in time between events or time until the next event, same thing, that's a theta that you're being given. If it's and a number of events per unit time, then that's a lambda that you're being given. And then you can flip back and forth between the two of them however you like. They're just the reciprocal of each other, making sure that the time is measured in the same units. So if it's minutes per event or events per minute, hours per event or events per hour, etc. Just make sure your unit of time is consistent between the two of them. So does that sort of help the question who asked that? Great. Awesome. Oh, nice. Okay. Question on the stream. Could you explain why Jensen's inequality is true? So, yes, I'll take a stab at it, like just intuitively. Like, I mean, I could prove it. I could look up the proof and then prove it for you here. I don't think I want to do that. That seems like not very much fun. But if you, like, I don't have the proof memorized, so I'd have to look it up. But if you sort of are looking for an intuitive sense, then I can do that. So the idea is, with this decreasing marginal utility, so it's not true for any function u, it's only true for u's. Oh, cool, someone posted a link to probably a proof of it, so fabulous. If you're welcome to check that out if you like, I'll check it out as well, and if it looks good, I'll copy it onto Piazza later. But sort of intuitively speaking, when you have a risk-averse individual, that's a person who would rather have certainty of money than uncertain money, basically, then the weights of the utility places on those higher values get kind of discounted. So if you're just looking at the average value of the wealth that's happening, you're going to basically weight each possible value equally. Like, let's say you had like a uniform distribution of what your wealth might be between like $0 and $1 million, then the $1 million and the $999,999 are worth the same as the $100,000 or the $10,000 or the $563,000, whatever. So if it's sort of an average, like, uniform distribution of wealth here, if you're just looking at the expected value, that's basically saying you weight each dollar equally in your mind. So like the next dollar is exactly as happy as the previous one. And then the expected value, so the utility of the expected value of that distribution would be the utility of right halfway in the middle, $500,000. But again, people don't really work that way. Like, you'd be so much happier getting to that first maybe $10,000 or $100,000 than the next little amount of that same. So like, getting the first $100,000 would be amazing. Getting the second $100,000 would be pretty sweet, like pretty awesome, but not as big a difference as going from 0 to 100,000. And then when you get up to like going from 900,000 to $1 million, by the time you're at $900,000, another $100,000 is kind of not as big a deal at all. So if we think about weighting by the utilities first, and then taking the expected value, those big values get down-weighted. They get a lesser weight on those values. And so when we take the expected value of that, once we've done that weighting of like bigger values getting slightly less weight, the average is going to be lower. So you would probably rather have a guarantee of $200,000 than a chance between 0 and $1 million, equally likely. Maybe. Again, everyone's utility function is slightly different, and there's plenty of experiments showing that sometimes people have inconsistent utility functions. So like, they'll prefer A to B, and they'll prefer B to C, but then they'll prefer C to A in a different framing. So there's some neat, you can look up economics utility functions. I'll see if I can find a cool a link for that. But thank you for that link there in the chat. It says an intuitive picture for a case for two things. Awesome. Thank you for sharing that. I think I'll just show how to write functions in R, because that's kind of cool too. So one cool thing about R, again, it has lots of functions built into it. It has all of the probability functions of all of the random variables you could ever want. It can do graphing, it can do all sorts of cool stuff. And it has normal functions built in as well, including things like factorial. So we can do factorial, you just do factorial of a number here. So if I run this, so that tells you that 10 factorial is 3,628,800. Pretty cool. But we can actually write our own functions, and the way to do that in R is as follows. If you want to create a function, you give the function a name, just call it my factorial, and then you write this arrow here, so assigning it to, and then you just type the word function, and then in the brackets you put whatever parameters you want. So that's the syntax for creating a function. So name of the function without the parameters beside it, left pointing arrow, function, and then in brackets whatever parameters you want. And you can have more than one parameter, of course, but for factorial we only need n. And then in curly brackets is where you put the code for your function. And you'll notice it's reasonably clean syntax. You don't need lots of semicolons or brackets or anything. You don't need to say like return whatever. It'll do that automatically, whatever the last thing you say is. If that's a command to output something, it'll just output that for you. And loops in R are pretty straightforward as well. So here's, again, a very crude way of calculating factorial. We can just set a temporary value equal to 1 inside this function, and then the syntax for a loop is just for I in 1 to n, and n here is just this parameter, whatever we've passed it. So whatever comes in, it's going to put it right there. And then in curly brackets, you want to say whatever you're going to do for each one of the loop, or for each step in the loop. So here we're going to say temp equals temp times I. So we can sort of trace this through. If we send my factorial of 3, then it'll set temp equal to 1. The first time it'll say temp equals temp times 1. Great. The second time it'll say temp equals temp times 2. So that temp will be 2. And then the third time through the loop, it'll say temp equals 2 temp times 3. So 2 times 3, so 6. And then once you exit the loop, then you just say temp and it'll return the result. So that's, again, the syntax here for this function, and I'm going to run it. So now that function exists, and now I can call that function, and hooray, we got the same result. We got 3,628,800. Now, I haven't done any error checking with this function. If I put in a negative value, I don't know what this is going to do. This is a badly written function. Don't use my code as an example. So I haven't done any error checking here at all. But what you would want to do maybe is to say n must be an integer. So if n is not an integer, then return some error message or something like that. I haven't done that, and I'm just going to be pretty basic with it. Okay, so that's cool. We know how to calculate factorial with a loop. But another way to calculate factorial is to use the fact that it essentially is a recursive function, right? Like if we want n factorial, that's just n times n minus 1 times n minus 2, da 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 da. So it's just n times n minus 1 factorial. So we can make use of that and write this as a recursive function instead of using a loop. And that's using the power of recursion. We basically call the function from inside the function itself. I have a cute story about that. But my daughter was 4 or 5 maybe, and playing this little coding game that we had. It was like an app called Lightbot, where you have to get this robot to go to different squares and turn on the light bulbs. So it was just teaching coding strategies to little kids. And she's doing this thing, and she's writing, proc 1 is procedure 1, and she goes, "Can we call proc 1 from inside proc 1? And me and my husband look at each other and we were like, oh my gosh, she figured out recursion. It was very cool. Also, fun fact, if you Google recursion, it says, did you mean recursion? And then if you click on that, it says, did you mean recursion? Neat little Easter egg there. Alrighty, so we can use recursion. We can make a recursive function to calculate factorial. We call the function from inside the function itself. So let's see how we can do that. I'm just going to call it, again, recfact, so recursive factorial. And again, the syntax to do this, you put the function name without the parameter, and then the arrow, and then function, and then the parameter, like that. And then inside the curly brackets, we need our base case, and then we need our recursive case. So the base case, obviously, we could say 0 factorial is defined to be 1. So this is an if-else. So if n is equal to 0, double equal sign is for checking whether something is equal. If we had put equals, that would have set n equal to 0, which we do not want. Then return 1. And remember, we don't have to say return. We could just say 1 and it'll return it. It knows what you want. And then else. So if it's not 0, then we're going to return n times the recursive factorial of n minus 1. So we're going to call this function from inside the function. And let's see how that goes. So I'm going to do that. I'm going to run this. So now that function is available to us to call, and yes, it worked again. 5,000. I want to break my R. Come on. Ah, okay. Stack usage is too close to the limit. So you can only recurse so many times in R. It's not going to go on forever, but anything reasonable, this will work just fine. Another thing we can do is think about using writing functions to calculate probabilities for random variables. So there's some other cool things that we can do. We can notice, so if we have a Poisson random variable, probability function, we know that the probability of Poisson random variable equals equals 0 is e to the negative mu. Right? That's the probability the Poisson random variable equals 0. And the probability it equals 1 is like mu to the 1 e to the negative mu over 1 factorial, which is just mu e to the negative mu. So I'm starting with 0, 1, 2, 3, etc. So the probability that a Poisson random variable with parameter mu equals 2 is mu squared times e to the negative mu over 2 factorial, but over 2 is great. For 3, we've got mu cubed, e to the negative mu over 6. For 4, we've got mu to the 4th, e to the negative mu over 24, etc. So we can think about this as like a sequence of values that are changing as as x increases. And then we can think about how this is changing. So to get from here to here, what we're doing is multiplying by mu, right? That's it. And to get from here to here, we are multiplying by mu. There's another factor of mu. And then we're actually dividing by 2. So we're multiplying by mu over 2. And then to get from here to here, we're multiplying by mu again. And then we're actually dividing by 3. Mu over 3. And then from here to here, we're multiplying by mu over 4. So we can actually see here that for this Poisson probability function, f of x, let's say, is equal to mu over x times f of x minus 1. Double check that for x greater than or equal to 1. You can double check that. So like if we want f of 2, it's mu over 2 times f of 1. Yes, that's right. So this is kind of like a recursive relation for the probability function of a Poisson random variable. Kind of neat. And so we could code that. We could put that into R. So I'm going to do that and show you how that works. We have this cool result here that the probability function at x is just the parameter divided by x times that probability function evaluated at x minus 1. And then, of course, our base case is going to be that f of 0 is e to the negative mu. Okay, let's code that. Turn this back on here. So we're going to notice that what we've found in terms of our relationship, and that we can write our recursive Poisson probability function here. Again, we say function, and then we give it the parameters that we want. And here we're giving it 2 parameters. We're giving it x and mu, because we need both of those to know. We need the parameter mu of the distribution, and then we want to know what do we want the probability that it equals. So we make our function. We have our base case. If x is equal to 0, again, with the comparison equals, double equals, then we let it equal e to the negative mu. And then otherwise, in the recursive case, we just return the recursive Poisson function evaluated at x minus 1, but with the same parameter mu, and then times mu divided by x. That's just using the recursive relationship we just found. And that's it. So that's pretty neat. And let's try that. I'm going to run that so that we have that function now available to us to use. And then we're going to test our function as well as the built-in function. So d plus is the built-in function with R. That's testing the distribution function. The first number you give is the x that they want, and the second number you give for dpois is the mean, the parameter for the distribution. And then let's test our recursive Poisson function. Yes, we got the same number, so it works. Pretty cool. So there you go. That's some examples of how you can write functions in R. Again, you don't need to write any of those functions because they're already built in. You don't have to, but that just shows you how you can create your own functions to do whatever you like. You can create functions to graph things for you. You can create functions to do, like, when you get up in higher level classes, like doing residual analysis, you can just create functions that are shortcuts to do stuff that you do a lot. Always good to document your code, as always, and have error checking if you can. Again, I was pretty lazy here. I didn't do any error checking. But this, again, just shows you how you can use recursion, you can use loops, you can use if-else, and you can build your own functions in R. Oh, don't forget, on the weekend, it is daylight saving time starting. That snuck up on me really fast. I forgot that that was coming up so soon. Someone kindly reminded me. So that means if you are in Waterloo or anywhere that observes daylight savings time, you will put your clocks forward an hour, or they'll probably go by themselves, honestly, and you lose an hour of sleep, which is too bad. I can't not afford to lose an hour of sleep, but at least it's happening over a 4-day weekend, so it's not going to be too bad. Hopefully you can afford to lose an hour of sleep over a 4-day weekend. If you are anywhere else in the world that does not observe daylight savings time, that means starting next week and for the rest of the term, everything will be happening an hour earlier for you than it used to be. So if, you know, these streams used to be at 3 a.m. for you, now they'll be at 2 a.m. I mean, I hope nobody is up right now watching this stream at 2 a.m. or 3 a.m. wherever you are, but if you are, hi! But everything will be, you know, if the assignment deadline was, you know, it's midnight EST, if that was for you 1 a.m. or 1 p.m., say, 1 p.m., everything is moving an hour earlier for you. So your deadlines will be up to noon now. They'll still be 11:59 p.m. for people in this time zone. It's just now the time zone is changing to Eastern Daylight Time, EDT, instead of EST. Things we never used to need to worry about before we had people all over the place at the same time. So please keep that in mind. Any deadlines from next week onwards are an hour earlier for you if you're not in a place that observes daylight saving time, and the same as they were before, but you've lost an hour of sleep if you do observe daylight saving time. Have a great break. I give you the same advice, but just maybe on a little bit smaller scale that I did over reading week, which is to make a plan to relax at some point this weekend. You have 4 days off. Hopefully you have not too much going on in all your classes, and hopefully you can make some time to deliberately relax, deliberately take some time for yourself, and get some sleep, drink some water, do some exercise. Now it's finally nice out here outside in Waterloo, so hopefully the weather's not bad where you are. And take care of yourselves. And then when you come back, you will have a few more things starting up again. So we'll have Mobius Quiz 5 opens on the Wednesday, but it doesn't close until the following week. And you'll also have, don't forget, your computer assisted assignment 2 is due next Friday. So you still have a week to work on that. If you want to get it done early, great. If you want, you can work on it into next week as well. So thanks everyone for tuning in. Have an awesome day. Have a great long weekend. I'll see you next week. Bye.